Complex numbers. Okay, so why do we need complex numbers? Why do we need imaginary numbers? Well, turns out that not all equations can be solved using real numbers. Not all equations can be solved using real numbers. However, we still want to solve these equations. So, for example, because the square root of any real number is always non-negative, meaning it is never negative, there is no real number x such that when you square it, you get -9, right? It is impossible to find a real number x such that when you square it, you get -9, or any negative number for that matter. So to solve this type of equations, we introduce the number I. However, this is not entirely artificial because those solutions that we get using imaginary numbers do have a meaning, like can be interpreted, and they can be used in many different branches of science and engineering, especially electrical engineering. Electrical engineering uses complex and imaginary numbers very heavily to model circuits, and they're used in circuit analysis. They're just as important as real numbers. Okay, so I mean they do have a lot of usefulness. Okay, so what is the number I? The number I is going to be a unique and special type of number with a property that when you square it, you get -1, which in other words is like saying I is the square root of -1, the principal square root of -1. So the number I is not a real number because when you square a real number, you cannot negative number. You cannot get -1. So it is not a real number. It is what we called an imaginary or complex number. Then the complex numbers are all the numbers that are of the form a plus bi, where a and b are real numbers. One possible interpretation of complex numbers is by thinking of them as points in the plane. So, for example, a complex number is going to be of the form a plus bi, as I said right here. So, for example, this is a complex number, 5 plus 3i. And you can think of these uh, complex numbers as points in the plane where the first coordinate is going to be this right here, which we call the real part. And then the y coordinate is going to be the 3, which this number right here in front of the I, which we call the imaginary part. Imaginary part. So complex numbers are really just can be thought of as just points in the plane. So if there's nothing weird with points in the plane, then there's nothing weird with complex numbers. They're really the same thing. You can think of this as just another interpretation of points in the plane. And in fact, so much so that the Cartesian plane that you're probably familiar with by now, the Cartesian plane is sometimes called the complex plane. Uh, when you want to think of points in the plane as complex numbers. When you're thinking of it in that from that point of view, we call the Cartesian plane the complex plane. Okay, the set of all complex numbers has its special symbol. It is a C. Okay, so we want to write it big. It will look like this. So it's like a C. All right. As I said, we write complex numbers in the form a plus bi. The a is called the real part, and then the b is called the imaginary part. That the a plus bi is called the standard form of writing a complex number. And the real part is denoted by RE. So the letters, the last letters of the alphabet, W, Y, W, V, W, and Z, those three letters are typically very popular for using complex numbers. So that's why I'm using the Z. So suppose Z is this complex number, then the real part, which is 5, that is denoted like this. The real part is 5, and the imaginary part is 3. Okay. Okay. So just making before we start with the problems, make a quick comment here on the history of the terminology. Complex numbers were originally called imaginary numbers. So the term complex number is the modern term for these type of numbers. Originally, they were called imaginary numbers, and the term imaginary number nowadays has a very specific meaning, which is slightly different from complex number. I will tell you in a second what that is. But they were originally called imaginary numbers by René Descartes, which was a mathematician and philosopher, French, very famous. And at the time when they were introduced and started being used, they were really poorly understood. And they were regarded by some people as mysterious, fictitious, or even useless, much as the negative numbers once were. So, once upon a time, negative numbers were also considered or regarded by some people as mysterious, fictitious, or even useless. But nowadays, we have found so many applications of negative numbers that nobody thinks of negative numbers in that way anymore. Nobody thinks of negative numbers as mysterious, fictitious, or even useless. In fact, we are so used to negative numbers nowadays that we don't even flinch when we run into them. So several scenarios, for example, just to name a few, in which we use negative numbers in daily life would be like temperature, right? Negative temperature is really, really cold, below 0, really cold. And then positive temperature, well above 0. And then other examples of negative numbers besides temperature. Let's say the balance in your account, your checking account. Positive means you have money. Negative means you don't you owe money, right? When you run in the red, they say that you actually spent more than what you have. Uh, so seeing a negative number in a checking account, you understand what that means. Also, let's say when we talk about elevation above sea level, positive would be that you're actually above sea level, and negative elevation would mean that you're below sea level. And those are just 3 examples. Negative numbers really are used uh, often in in real life, in daily situations. And nowadays, it is the same for complex numbers. Although when the situations in which complex numbers are used are typically not studied, or people don't run into them as often because they're like specialized, like they're like, electrical engineering or physics or stuff that are more specialized. But they are used so often nowadays that we don't think about them as weird or mysterious or fictitious or useless anymore. Okay. Oh, and before we start the problems, so what does the term imaginary number mean nowadays? So I put footnote there, 1. So nowadays, the term imaginary number actually means a special type of complex number. It is a complex number that doesn't have a real part, where the real part is 0. So it is a complex number of the form just like that, 3i. So this one would be a complex number. This one is like a imaginary, or if you want to be very specific, purely imaginary. All right, and that would be complex. But of course, people sometimes abuse the terminology and just say imaginary for either type, and that's fine. Okay, so even though we don't have those misconceptions about complex or imaginary numbers anymore, unfortunately, the name stuck. Okay, now dealing with complex numbers is actually very easy because you treat the I in exactly the same way as if it were a variable. So you're gonna treat the I like if it was a variable, and you're just gonna do everything as usual. You're gonna add as usual, subtract as usual, multiply as usual. The only thing is that that once you have simplified as much as you can, you're gonna take it a step further in the simplification process, and every time you see an I squared, you're going to replace that with -1 because I squared is -1. So then you do that replacement, and then with that you simplify a little bit more, and then that's it. That would be the end. So for example, let's compute the following. So 3 plus 2i plus 5 minus I. So again, remember, we just treat this like a variable. We collect like terms. So things that don't have an I are like terms, and things that have an I are like terms. So we're combining the 3 and the 5. That would be 8. And then the 2i minus I, that would be 1i. And again, we usually don't write the 1, so we just write I. And that's it. That's all there is to that. Add the constants, the real parts, the terms that don't have I, and then add the imaginary parts, the terms that have I. Okay, and that's it. Now for subtracting, same thing, but remember that a minus in front of a parentheses distributes, so everything needs to change sign. So let's change that minus to a plus, and then distribute the minus, so that becomes -5, and then the minus I becomes plus I. And now we collect like terms. 3 and -5 is -2, and then 2i and I is 3i. Okay. All right. Multiplying. So let's multiply these ones. Again, we just treat the I like if it was x. So we're going to do the FOILing uh, and collect like terms. So 3 times 5 and 3 times -I, and then we do this. So this is going to be 3 times 5 is 15. Then 3 times -I is going to be minus 3i. 2i times 5, that's 10i. And then you see the very last one is the one that gives you I squared. 2i times -I, that would give you -2i squared. That gives you -2i squared. Okay, now combine any like terms that you can. So this is going to be 15. I can combine these two, so that's going to give me plus 7i, minus 3i and 10i, 7i. And then here, you see the I squared, we're going to replace the I squared with -1. So now the I squared is going to get replaced with -1. Okay, and then what is that? That would be 15 plus 7i. -2 times -1 is going to be +2. And then we can combine the 15 and the 2 to get our final answer. 15 plus 2 is 17. So 17 plus 7i is our final answer. Okay, at this point, try to do this one on your own. Pause the video and FOIL this and simplify it as much as you can, and then compare notes with me. Okay, let's do it. So FOIL or multiply. This is going to be 4 times 4, 4 times negative I times 4, I times negative I. So this is going to be 4 times 4 is 16, and then 4 times negative I is minus 4I. I times 4 is plus 4I, and then I times negative I is minus I squared. Okay. Note that the two terms in the middle actually cancel each other out. You have negative 4I and positive 4I, though that gives you 0I. And 0I, you don't have to write that because it's like 0x. You don't write 0x, you just write that's just a 0. It doesn't do anything. So that means the two in the middle cancel and you end up with that. Okay. Now I squared is negative 1. So the minus in the middle stays, but then the I squared gets replaced with negative 1. So that's like minus negative 1, which is 16, plus 1, which is 17. So the final answer is 17. So note that we multiplied two imaginary numbers, two complex numbers, and we got a real number. So that happens whenever you multiply a number by its so-called conjugate. So what is the conjugate of a real number, of a complex number? Well, the conjugate of a complex number is basically another complex number that has the same, that uses the same numbers, but the sign in the middle is changed. So if you have a complex number like this, a plus bi, then the complex conjugate, or just conjugate for short, is going to be the complex number a minus bi. So you see, you still have the same a and b, but the sign in the middle is changed. That is the complex conjugate. So for example, what is, and by the way, the notation that we use is a bar over the complex number. So we use a bar. That means the conjugate. That means the complex conjugate. All right, so this means find the conjugate of that. So the conjugate of that is the same numbers, just the sign in the middle is changed. So 5 minus 2i would be the answer. And that's that. That's the complex conjugate. What is the complex conjugate of 1 minus I? Well, same thing, but just the sign in the middle is changed. So it would be 1 plus I. And what do you get when you multiply 3 plus I by the complex conjugate of 3 minus I? Okay, let's work this out. This means 3 plus I times the complex conjugate of this, but the complex conjugate of that is going to be the same thing, but with a plus. So that means it is this, 3 plus I again. Okay, and now you multiply this. 3 times 3 is 9. 3 times I is 3I. I times 3 is 3I. And I times I is I squared. Okay, now we simplify. We collect like terms. So this is 9. 3I and 3I is 6I. And then the I squared gets replaced with negative 1. So collect like terms and replace the I squared with negative 1. And then 9 and negative 1 gives you positive 8. So 8 plus 6I. Okay. Now you should pause the video and try to do that one on your own and compare notes with me. So what happens when you multiply a complex number with its complex conjugate? Okay, let's do it. This is going to be a plus bi, and then what is the complex conjugate of that? That's going to be same, but sign in the middle is changed. So like that, a minus bi. And now when you FOIL this, you're going to get a squared, because a times a, and then a times negative bi, that's going to be negative abi. This one, bi times a, is positive abi, and then the very last one, you're going to get minus b squared I squared. You have two b's, so that's going to give you b squared, and you have two i's, so that's going to give you I squared. And then positive times minus is minus. Okay, so that's what you get. Note that the two terms in the middle are actually identical, but with opposite signs. So they do cancel each other off. So that's going to give you 0. And then you're going to be left with a squared minus b squared I squared. But I squared should be replaced with negative 1. And then you have a squared plus b squared. And that is the final answer for that. And note that there's no i's, there's not an I in the final answer for that, and that happens all the time. Whenever you take a complex number and multiply by its conjugate, you're going to get the real part squared plus the imaginary part squared, no I, okay, just the b squared. And that formula is useful enough that it's something that you should consider memorizing. Okay, we're going to be using it more in a minute, but is very useful. Okay. Before we get to the application of that formula that I just mentioned, that you should consider memorizing, that appears when you're dividing complex numbers, when you divide one complex number by another. Let's take stop for a second and let's talk about square roots of negative numbers. That's another instance in which imaginary numbers appear. So if you have negative number, something like this, and you're taking the square root, that is typically simplified in terms of imaginary numbers. So how do you simplify the square root of a negative number? This is how you simplify it. So the square root of a negative number, let's say negative a, is by definition going to be the square root of the positive number without the negative sign times I. So a quick example would be, let's say, square root of negative 5. How is that simplified? That is just the square root of 5 and then I times I. And the I, notice that the I is outside of the square root, not inside. Okay, you have to write it outside. I've seen many students when they're doing the homework online do this fine, and then when they enter it, they put the I inside the square root, and of course it's going to mark it wrong. Um, so be sure to write the I outside. So another example, negative square root of negative 6. That what does that mean? That means the square root of 6 I. Okay, so that's how you're always going to translate this, the square root of a negative number. You're going to always translate it like square root of the positive number without the negative sign times I. Okay, And here's a warning: when you're dealing with square root of negative numbers, please be mindful that the familiar rules that we learned for multiplying square roots does not work for negative numbers. Okay, it only works when the numbers are inside. So what do I mean by that specifically? So for example, square root of 2 times square root of 5, you could simplify this into a single square root by saying this is square root of 2 times 5, which is 10. So this is true. And similarly, you could go backwards. You could break it up if you wanted. So square root of 14, you can say that this is square root of 2 times the square root of 7. That is also true. However, you cannot do this with negative numbers. So it is not true that if I have the square root of 5 times the square root of negative 5, you cannot say that this is the square root of negative 2 times negative 5, which is 10. That is not true. You cannot multiply square roots like that the way you would do it if they were positive numbers. So that is not true. Okay, that rule does not apply anymore with negative numbers. So how do you do that then? How do you combine these? Well, the trick is to first use this translation and then work with them. So here is how you would do it with these concrete examples. Square root of negative 4 times square root of negative 2. What's that? Okay, so the way to do this is you're gonna first translate it like this. So square root of negative 4 means square root of 4 times I, and square root of negative 2 means square root of 2 times I. So that would be the first step. You pass through the definition and convert it in terms of I. Then you can because now these square roots have positive numbers inside, now you can combine them if you wanted to. But square root of 4 is actually 2, so I can just write 2. That would be a lot better than combine it with another radical. I'm just going to write 2. Then you have this square root of 2, and then you have the two i's, so that would be I squared. Now, I squared is negative 1, so that means it's going to be negative 2 square root of 2. And that would be the final answer for that. Okay, let's take a look at another one. Square root of negative 8 times square root of 2. Square root of 8 times the square root of negative 2. Okay, first we do the translation thing. So this is what? This is square root of 8 times I. And then what is square root of negative 2? Square root of negative 2 means square root of 2 times I. And now you can combine these square roots because they have positive things inside. So square root of 8 times square root of 2, that's square root of 16. 8 times 2 is 16. And then times I squared. Now square root of 16 is 4. I squared is negative 1. So this is negative 4. Okay, and that is the answer. Okay, now let's do the next one. Set square root of negative 40 minus the square root of negative 10. So square root of negative 40, what does that mean? That means square root of 40 times I. And so you have these minus, and then square root of negative 10, what does that mean? That means square root of 10 times I. Okay, and now you simplify this if you can. Square root of 40 can be simplified by breaking it up into square root of 4 times 10. So 40 is 4 times 10, and 4 has a square root that is a whole number, so that's why we break it up like that. I, and then 10 cannot be broken up in such a way that it simplifies anything, because 2 and 5 don't have square roots that are whole numbers. So you just leave it as square root of 10. Now, square root of 4 is 2, so that's going to become 2 square root of 10 I minus square root of 10 I. And note that these two things are actually like terms. Square root of 10I, you have 2 square root of 10I minus 1 square root of 10I. So you see these are like terms because the square root of 10I is repeated in both of them. So this is pretty much like having 2 of something, 2m minus m. So it's like having that, 2m minus m, which is just m. So these are like terms. So 2 square root of 10I minus square root of 10I is just going to be square root of 10I because they're like terms. The m is like the square root of 10I. Okay, and that is the end for that. We cannot simplify any further because, as I said, 10 cannot be broken up into a useful way. Okay, now I recommend that you pause the video and attempt the very last one on your own. And then compare notes with me. Okay. So what is this? This is negative 2 plus, what is square root of negative 5? Square root of negative 5 means square root of 5 times I. All right, and then now we can square this. Instead of writing it out twice and foiling, there's two ways of squaring something, a binomial like that. You either write it out twice and do the foiling, blah blah blah, or use the shortcut. I like using the shortcut, so I'm gonna use the shortcut. What is the shortcut? If you're squaring two things, here's a binomial. Here's a shortcut. Square the first one, square plus square the last one, the second one. So a squared, b squared, and then there's a term in the middle which is multiply a and b and double it. So ab doubled would be 2ab. So I'm gonna use this shortcut. Okay, so what do I get when I use that shortcut? Square the first, square the second, and then there's a term in the middle that is multiply both of these and double it. So if I multiply these two and double it, you multiply, you're going to get negative 2 square root of 5I, and double instead of negative 2 is going to become negative 4. So negative 4 square root of 5I. Okay, and you can check that if you write it out twice and FOIL, you get the same thing. I mean, after simplifying. So this is going to be 4. What is this? It's going to be negative 2 squared is negative 4. Positive 4 minus 4 square root of 5I. And then how do you square that one? Well, you square both of them. Square root of 5 squared is actually 5, and then you get I squared. And there's one more thing we can do. We can replace the I squared with negative 1. So this is going to be 4 minus 4 square root of 5I. And then the I squared gets replaced with negative 1. So this is going to become negative 5. And then you can combine the negative 5 with 4. 4 and negative 5 is negative 1. So this is negative 1 minus 4 square root of 5I. And that would be the final answer. Okay, now the last thing about complex numbers is how to divide them. Okay, how do you divide complex numbers? To divide complex numbers, use the formula that I told you about. That was the result of example 2D, that right there. So I wrote it out separately in its own formula because I said it's useful and you should consider memorizing it. Okay, and it says that if you take a complex number and you multiply it by its conjugate, so change the sign in the middle only, you're going to get the first number squared plus the b squared. Remember, there's not going to be any i's, and the thing in the middle is always plus. If you put a minus, you did it wrong. Okay, so that formula is what you use for dividing complex numbers. And how do you put it to use? Here's how you do it. What we do is we're going to multiply the bottom. If the bottom has any i's in there, you're going to take the bottom and multiply it by the complex conjugate. The complex conjugate of 1 plus I is going to be 1 minus I, and whatever you do to the bottom, you have to do to the top. So multiply top and bottom by 1 minus I in this case. Alright, and now, using the formula, on the bottom you're going to get the first number squared plus the second number. The second number is what is in front of the I, the imaginary part. What is in front of this I is a 1. So 1 squared. Remember, there's not going to be any minuses or any i's once you apply the formula. So it's going to be 1 squared plus 1 squared in this case. And on the top, well, I'm just going to write it out like that. Multiply across. 2 times 1 minus I. And what do you get? You get 2, 1 minus I on the top, and on the bottom you get 1 plus 1, which is 2. And now I can cancel those 2. And the final answer would be 1 minus I. Your answer should always be in the form a plus bi, because complex numbers are always expressed in their standard form, meaning in the form 1 plus bi, or 1 minus bi. Okay, so how about this one? So same thing. I'm going to copy it again for a second for my convenience. And then we're going to multiply top and bottom by the complex conjugate of the bottom. The complex conjugate of 3 plus I is 3 minus I. So multiply top and bottom by 3 minus I. On the bottom, the effect of that is that you're going to get the first number squared plus, always a plus, the imaginary number, the imaginary part squared. The imaginary part is the coefficient of the I, the number in front of the I, which is an invisible one. So 1 squared. Again, no minuses, no i's in that result when you apply the formula. So just 3 squared plus 1 squared. And then on the top, I'm just going to write it out. Okay, now on the bottom, you're going to get 10, because 3 squared is 9 plus 1 is 10. And on the top, you still have this. Okay, we cannot leave it like that. We have to keep going, because we want the answer in the form a plus bi. That obviously doesn't look like that yet. Okay, so we have to FOIL the top, multiply the top. 2 times 3 is 6. 2 times negative I is minus 2i. 3i times 3 is plus 3i. And then minus, because positive times minus is negative, and I times I is I squared. Okay, and then on the bottom you have 10. And now, simplifying the collecting like terms, the terms in the middle, that's going to give you 1i, or just I, and then minus I squared is going to be negative 1, and then combined with the minus is actually plus 1. Is minus negative 1, which is the same as plus 1. And now combining the 6 and the 7 and the 1 is 7. And this is what you get. Note, however, that even though we cannot really simplify anymore, there's nothing I can cancel. Uh, we cannot simplify anymore. You're still not gonna report the answer like this because this is not in the form a plus bi. This is not in the standard form. This is, you compare, this is not in this form. It has to be, sorry, this form. It has to be something plus a number I. That's not like that because there's the whole over 10 thing. So what you do is then you split it up, split it up, split it up. So this is going to be 7 over 10 plus I over 10. Split it up like that, separate them. 7 over 10 plus I over 10. And then right to the I a little to the side. So this is going to be 7 over 10 plus 1 over 10 I. Those two things are the same. You can just pull out the I to the side and leave a 1 there. Okay, and that is the way you're going to report the answer. That is in standard form, a plus bi. Okay. Now you should pause the video and try to do the very last example. That is the very last example. Okay, let's compare notes. This is going to be 5 minus I over 2 minus 3i times multiplied by the complex conjugate on the top and the bottom. The complex conjugate at the bottom is 2 plus 3i. And then the bottom is going to become the first number, the real part squared, which is 2 squared, and then plus, always a plus, and then the 3, which is the imaginary part, the coefficient of the I, squared. No i's, everything is positive, remember. So, and actually, you could write negative as well, as long as you put it in parentheses, but in the end, everything is going to be positive. When you square negative 3, you're going to get positive 9. Okay, so that's going to be positive 9. So that's going to be 4 plus 9. Okay, and then on the top, you just multiply across. Now, what do you get? Well, we have to for the top. 2 times 5, or 5 times 2 is 10. 5 times 3i is 15i. This would be negative 2i, and this would be minus 3i squared. All that over 13. Now, collect like terms, simplify as much as we can. The 2 in the middle give me 13i. And then this is going to be minus 3, and then I squared gets replaced with negative 1. And then this is the same as plus 3. Negative 3 times negative 1 is positive 3. Then you can combine the 10 and the 3, and that gives you 13. Okay, and that's not in standard form. That's not good. Remember that you cannot cancel, because the only way you can cancel things is if you have factored them first. So I can, before I can cancel a 13, I have to factor it out. Factor the top. If you factor the top, that would become 13, 1 plus I over 13. Now we can cancel. You can never cancel before you have factored. Remember that. You can never cancel anything in a fraction before you have canceled. So you factor the top, before you have factored. You factor the top, then you can cancel. So we factor the top, then we can cancel. And the answer is 1 plus I. And now, notice that that is in the standard form. And that is the final answer. Okay? So that completes the lesson. Now, one thing uh, before I conclude it is one comment here that even though we won't be making much use of the following facts, is something you should probably know, nonetheless, is that if you have two complex numbers, then we really, that are in standard form, we say that the complex numbers are equal if and only if all the numbers involved are equal. The real parts are equal and the imaginary parts are equal. So A has to be equal to C and B has to be equal to D. The corresponding parts have to be the same. And that completes all the basics about complex numbers.